Alright, these are the answers to the Chapter 10 test. Let's get started. On number 1, the answer is lateral edge. Two, a sphere. 3, the altitude of a pyramid is a perpendicular segment. From the vertex to the plane of the base. Alright, on to our next ones. For problems 4 and 5, we want to find the volume. For problem 4, it's a cylinder, so we can use the volume formula, which is pi r squared times the height. So in this case, when the radius is 9 squared times 28, we're able to find that the volume is 2,268 pi. On number 5, we have a cone, so on our volume equation we want to make sure that we start off with a 1/3 pi r squared times the height. And so we have 1/3 pi. The radius here, notice that the diameter is 30, so the radius is 15. So we have 15 squared times the height, which is 10. Simplify this, we should find that the volume is 750 pi. Alright, on to the next problems. Alright, on 6 and 7, again we want to find the volume. So for 6, we want to use the equation volume is 1/3 because it's a cone, or sorry, it's a pyramid. And then the area of the base here is a trapezoid. So we have, I'll just go ahead and write it out here. 12 plus 20 over 2 times the height. And notice the height in this case is 8. So times 8. So that's 1/3 area of the base times the height, which is 24. So we find here that the volume, is 1/3 of 32 over 2 is 16. 16 times 8 times 24. And here we're able to find that the volume is 1,024 cubic centimeters. Sorry, on those other problems, make sure that you get the correct units as well. Cubic centimeters. Alright, number 7. The volume of this sphere is, of this hemisphere is 2/3 pi r cubed. Remember, it's 2/3 because we're dealing with half. If we're dealing with a full sphere, then it's 4/3. So when we substitute in, we have 2/3 of pi, and our radius here is 15. So we have 15 cubed. So remember, 15 cubed is 15 times 15 times 15. And so we're able to find that the volume is 2,250 pi. And so that's that part, 2,250 pi cubic centimeters. On the surface area equation, I'm going to write this out. Surface area of a sphere is 4 pi r squared. But surface area of half a sphere is 3 pi r squared. Now you might ask, why 3 pi r squared? Well, if you cut the surface area, if you cut a sphere in half, right, you have 2 pi r squared. But we have this base section. And when we're dealing with surface area, we do need to calculate that in. The area of that base is a circle, so we add in 1 more pi r squared. So the surface area of a sphere that we're going to deal with, 3 pi r squared. So when we substitute in our values, 3 pi times 15 squared. We get that the surface area is equal to, I got 675 pi square centimeters. Make sure you get the squared centimeters on there. So that's the answer right there. All right, on to the next problems. All right, on 8, I'm going to go ahead and start with an equation here. I'm going to start with 195.3, which is the volume of this, is equal to our volume of equation for this pyramid. 1/3 area of the base times the height. Right? Remember that big B is area of the base. So let's go ahead and substitute in what we have. 195.3 is equal to 1/3. The area of the base, I'm going to break this up into 7 times C, and then times the height, which is 9. Okay, so let's cancel out the 9 by dividing both sides. Divide by 9, divide by 9, and we find that I don't have that exact calculation on hand. Let me just get it. 195.3 divided by 9. We got 21.7 is 1/3 times, I'm going to call it 7C. And now to cancel out the 1/3, we want to multiply by 3. So times 3 is 65.1 is equal to 7C. So now divide by 7 on both sides, and we find that C is equal to, I get 9.3. So 9.3 centimeters is this length right here. 9.3. All right. On to number 9. And on number 9, I'm going to start with just a general equation here. This the volume of this inside region, the region between the cylinders. So I'm going to say volume inside is equal to the volume of the big cylinder minus the volume of the small cylinder. Alright, so we want to find the volume of the big cylinder, volume of the small cylinder, and then go from there. So let's work here. And sorry, actually, let's go ahead and take our 336 pi, substitute it right here. So we have 336 pi is equal to volume of the big cylinder is pi r squared h, and then minus small cylinder pi r squared, and then times the height of that. So here we have 336 pi equals, and now let's go ahead and substitute in the radius of the big cylinder. Notice the diameter is 16, so the radius here is 8. So we have pi times 8 squared, and then the height on this, that's what we're looking for, h, minus pi, the radius on the small cylinder, the diameter is 8, so the radius here is 4. So we have pi times 4 squared h. Let's go ahead and simplify. 336 pi is equal to 64 pi h minus 16 pi h. Okay, now we have 64 pi h's. We're subtracting 16 pi h's. What we get is 48 pi h's. So on this side, we're left with 48 pi h, and on this side, 336 pi. Right, last step is dividing both sides. I'm going to go ahead and change colors here. Divide both sides by 48 pi. Notice the pi's cancel out, and we're left with the height is equal to 7 centimeters. All right, on to the next problems here. All right, here on problem number 10, we want to find the length of each side of this equilateral triangular based pyramid. So I'm going to draw a couple pictures here to start. Let's go ahead and draw this this pyramid to start. And I'm going to do my best. Obviously, I don't have the greatest skills, but just bear with me for a moment. So we have this pyramid. The base is an equilateral triangle. I'm drawing it to perspective here. And then the height, we know the height of this triangle, triangular pyramid is 16 centimeters. Okay, yeah, not the worst, not the best, it'll do. All right, so let's go ahead and write out our equation for this pyramid. The volume of a pyramid is 1/3 big B, or area of the base, times the height. But we're given the volume of the pyramid. It's 48 square root 3, so we can substitute that in. 48 square root 3 is equal to 1/3 area of the base, and we're given that in this situation the height is 16. Right, so we want to cancel out and solve for the area of the base. So we want to divide by 16, both sides, then multiply by 3. We find that the area of the base is 9 square root 3. Right, again, this is the area of the base. All right. Now, what is the area of the base? That's comprised of a couple things here, right? It's 1/2. It's a triangle base. So let's go ahead and just call this whole length right here. So this whole length right here, we'll call this B, right, for base. Right? But if this whole length is B, notice we can take this equilateral triangle. This is 60. This is 60 and 60. Bisect that angle, and notice what we get. A right angle here, and here a 30-degree angle. All right, so we have a 30, 60, 90 triangle. Right, so if this base is B, then this half of the base, we can call 1/2 B. So I'm going to write that up. Half of the base is 1/2 B. Right, this is equilateral triangle, so this is B. This length right here we know is B, and that follows along with our 30, 60, 90 rule. So the height of our triangle, therefore, is this length right here times square root 3. So the height is 1/2 B square root 3. All right, so let's go ahead and just look what we have here. The area of the base is 1/2 base times height, right? Because it's a triangle. But the area of the base, we're given that. You know, it's 9 square root 3. So we're going to substitute that in. 9 square root 3 is equal to 1/2 the base. We call that B. And then the height in this case is 1/2 B square root 3. 1/2 B square root 3. Right, that's the height of this triangular base. All right, so let's go ahead and simplify here. 9 square root 3 is equal to 1/2 times 1/2 is 1/4. B times B is B squared, and then we have this square root 3. Okay. To simplify this, just notice you have square root 3's on both sides, so we can cancel that out, and we're left with 9 is equal to 1/4 of B squared. Go ahead and multiply by 4 on both sides. Get that 36 is equal to B squared. Square root both sides and find that B is equal to 6. Right? Or in other words, each of these side lengths, right, this B is 6. So this length right here is 6 and 6. All right, and that's it. On to the next problem. Alright, on this next problem we have a scoop of ice cream and a cone. We want to see if the scoop will fit inside or not. So let's go ahead and compare the volume of the scoop and the volume of the cone. First of all, let's look at the scoop. And it's a sphere, so our volume is given by 4/3 pi r cubed. Right, so let's go ahead and just substitute in what we know. Volume is 4/3 pi. The scoop, it has a diameter of 6, so the radius is 3 cubed. So 3 cubed is 27 times 4 divided by 3. Here we get that the volume is equal to 36 pi cubic centimeters. Alright, so that's the scoop. Now let's look at the cone. On the cone, its volume is 1/3 area of the base, or pi r squared, times the height. So let's again substitute in what we have, 1/3 pi, and here the radius is going to be 2.5, right, because the diameter is 5. So 2.5 squared times the height, which is 10. Alright, so here we are, 2.5 squared times 10 divided by 3, and pi of that, we get that the volume is equal to about 20.83 pi. Right, so to answer this question, is the cone big enough? We can say no. Right? The ice cream will fall out. The scoop has a volume. The scoop's volume is greater than the cone. Alright, so that's the problem right there. Alright, number 12 was extra credit, so we're going to go ahead and skip through that, but it's not too bad. 30, 60, and 90 triangle, which brings us to the challenging problem, or the intimidating problem of the test, but you'll see it's not too bad. Number 13, we want to find the area of the shaded region. Let's go ahead and just write out in words how we're going to do this. Just notice that the area of the shaded region, right, area of the shaded region is equal to the area of the big hexagon, right, that outer hexagon, minus the area of the small hexagon. Right, so we're taking, now we have this region in between, and we want to take that region in between and divide by 6. Right, so to find the shaded region, we need to find the area of the big hexagon, area of the small hexagon. So let's go ahead and do that. Let's start out with the area of the big hexagon. Alright, now notice on this big hexagon, we're given this length is 6. So let's just look at one of these triangles here. Alright. So on our big hexagon, we can see this triangle right here. The height of this is 6. And there's a fact about regular hexagons that you need to know, right? And that's that these triangles are equilateral. So this length is congruent to this length, which is congruent to that length. These are all 60-degree angles. When we bisect this 60-degree angle, remember we get a 30, 60, 90 triangle. So here, actually I'm going to just make this a little bit cleaner. Right? Notice that this right here becomes 30, this is 60, and of course this is 90. Right? So no, look, 6 is the a square root 3 type value. I'm going to go ahead and write that up. You know, a square root 3 is 6. So let's go ahead and just write out that part here and say 6 is equal to a square root 3. So divide by square root 3, divide by on both sides. We get that a is equal to 6 over square root 3. But we could just multiply by square root 3 on both sides. Square root 3 times square root 3 to rationalize the denominator, find that a is equal to 6 square root 3 over 3, right? And notice the 6 and the 3 cancel out, so we find that a in this case is equal to 2 square root 3. All right, so what does that tell us? That tells us that this length is 2 square root 3. This length is 2 square root 3. Right, so this whole length here is 4 square root 3. So what's the area of that big hexagon? Well, it's 1/2 times the base, which is 4 square root 3, times the height of that triangle, which is 6, times the number of triangles, 6. Right? So we find that the area of that big hexagon is 72 square root 3. All right? So we got that part. Check it off. Now the area of the small hexagon. Right? And again, this is going to be a similar kind of process. Let's just remember here that I'm actually going to erase what we have. Actually, I take that back. I'm just going to work on this side. Remember, this length right here is 6. So let's get this length right here. Notice we've got one triangle of the smaller hexagon. So this is 6 and this is 6. We can bisect this part here. We know this is a 90-degree angle. Again, this is 30, 60, 90, 30, 60. So if this length is 6, then this length right here, I'm going to put it in a different color, is 3, right? Because 3, 6. And then this length right here is 3 square root 3. Right? So let's go ahead and just get the area of that small hexagon. Well, it's the area of this one triangle, or 1/2 times 6 times 3 square root 3 times the number of triangles, which is 6. Right? And we find that the area of the small hexagon is 54 square root 3. All right. Now we found both pieces of information that we needed to have to solve this problem. So let's go ahead and just substitute this in over here. So the area of the shaded region is 72 square root 3 minus 54 square root 3 over 6. So let's go ahead and simplify this down. 72 square root 3's, 54 square root 3's. Let's see. Gives us, let's see, 20, my mind is blanking, 18 square root 3 over 6. 18 over 6 is 3, and so we have 3 square root 3 is the area of that shaded region. You did it! So that's it. Alright, that is the test. If you have any questions, let me know. And thanks for watching.